So we envision in our grand simulation suite in ISEC many different models for space elevator simulation. And I have been working on one for a while now, and I'll tell you a little bit about that. First, I'm going to talk about why we need the simulations and some approaches to the simulations that exist and that we're going to try. And then I'll talk about the one that I'm working on, which I'm going to call the distributed mass mergeable string model, some early results, and then some conclusions. So the various types of simulations that we need to do in space elevators come into three categories. One is deterministic. So if you look on the left-hand side, it's basically a vibrating string, and to a good approximation, space elevator tether is going to be just like that. So it will have normal modes of oscillation, it'll be under tension, and we want to be able to predict the position of any point along the tether with a good degree of accuracy. So that's the deterministic, and I'll be talking about that for the rest of the talk, but I just wanted to mention that we will also have to do radiation transport. So Pete showed this plot earlier before. We have the space elevator extending beyond the bow shock of the Earth, and it's in a rather intense radiation environment, so we'll have to do radiation transport simulations. And this is not deterministic, this is stochastic. You have to do radioactive decay and radiation effects and things like that. And then finally, we do not yet have a lot of material parameters for graphene and maybe some other materials which we might use for the tether. And so it would be a good idea if we did some macromolecular simulations. Ultimately, this comes down to a quantum calculation of all the atoms in the sample. And hopefully from this, we can extract some material parameters. But that's all for the future. As for the current model, the tether is fixed to the Earth's surface, and it will have some distribution of mass, which, if you follow the constant stress model of Pearson, it has a taper, which kind of looks like the blue lines that I've showed on the right-hand side. And there will be some climber going up and down with an apex anchor at the far end. And we want to be able to predict the motion of the tether under gravity and centrifugal force and all other forces that we think are important. And we'd like to know what the strains and stresses are all along the tether. The approaches to this problem are varied, and lots of people have worked on it. Probably the most common, because it is the simplest, is the point mass and massless spring model. So this is what you've all encountered in your university physics course. Divide the tether into segments, and then further collapse these segments into dimensionless masses. So all the mass is concentrated at a point. Relatively easy to implement. If you go to the full dynamics, or something which is much more realistic, you'll have to do something like continuum mechanics. So you'll have a continuous tether, and you could use finite element analysis to solve the deformation as the climber goes up and down, or forces are exerted on the tether. And because we're going to have deformation problems and have to predict those and solve those, small deformation systems like finite element analysis may not be sufficient. We would probably have to go to something like absolute normal coordinates. And this is good for large deformations, so we may have to deal with twisting and mass flow and things like that. There's I think probably a unique model, and Jim Dempsey is going to tell us a little bit about this, his version of GTOS. So this is the so-called point synthesis model. The tether is represented by point masses, but they move around in order to form the continuous mass distribution of the tether. And that is actually a well-validated program by NASA And it is something that Jim is using now to do some space elevator simulations. So onto the distributed mass model. This is what we do. I think this is a model which is kind of independent between the point mass model and the continuum model. One of the advantages of this model is that it has many smaller discontinuities than the point mass model. So obviously, if you're moving up a tether and you come into a concentrated mass point, that's a discontinuity. And then you're going into the massless spring, and that's a discontinuity. Also, I think fewer nodes, that is joints between the springs, are needed to solve the problem, and that would speed things up quite a bit. Disadvantages of this model, realistic springs require a lot more complicated equations of motion, and I'll show you this in a minute. And this model, I believe, can't really handle large deformations. So if you have serious buckling, if it doubles over on itself, that's way more nonlinear than I was anticipating. And this really is a model that I'm developing here in which we can analyze so-called standard behavior of the tether. And if you look at the translation here from the diagram over to the set of continuous springs, each segment is divided into each tether is divided into several segments, typically 1,000, and each segment has a spring constant, a mass, and a length. And then somewhere in the middle is the climber mass, and that has to be simulated. So let's don't worry too much about this. I just put here the Lagrangian, so it's a way of writing down the energy of the system. You need the kinetic energy, you need the potential energy, and if you were just using a point mass, massless spring situation, this would be a lot simpler. So for the potential energy, you just have the spring terms down below, the gravity term, the last two lines would just be your simple gravitational constant times the mass divided by r squared, but you see, divided by r. But you see here that it's gotten much more complicated because we have to integrate over the shape and space of the tether. And one more interesting thing is the kinetic energy. So if you write down the kinetic energy, you're expecting a term like 1/2 mv squared, and instead you see this factor of 6 coming in. And the reason for that is that you have an extended mass spring. And so not only do you have 1 second derivative that you have to put in your Runge-Kutta, you have 3 for each node that you're solving for. And these are coupled, so that adds the complication to the solution of the problem. And then we go ahead and solve the Euler-Lagrange equation to get the equations of motion. So I mentioned that we have about 1,000 nodes, could have more. The more you have, the more like a continuous system it behaves. And then you have to solve the matrix equation for all these equations of motion for each time step. So you integrate the equations of motion to get the position and the velocity, and I'm using a 4th order Runge-Kutta method for this. There could be other ways to do it, perhaps more efficiently with backward differentiation models and things like that, but I'm starting with something I know. An extra complication is putting in the climber. So my first attempt at this problem was a tether with no climber. And that went really smoothly. I got it working pretty quickly. I got all the oscillations going and everything made sense. And then I put on the climber and I ran into more and more problems, and the problem became more difficult putting in the climber. So if there's a climber on a spring segment, you have this particular problem. You've already divided up the tether into several segments. And those segment boundaries, although artificial, are necessary for discretizing the problem and solving it. However, when the climber gets to the edge of one of these segments, the spring constant for the part above the climber gets very, very large, and the spring constant below gets small, and you wind up with a situation where you are getting into nonlinear territory, and the Runge-Kutta sort of says, I don't know what to do. It starts putting in artificial oscillations and sometimes even crashes. So what do? You say, well, okay, when it gets to to the edge of the boundary, it just merges the remainder, the small part of the segment, with the segment above it. So now you have a nice long section. You don't have any outlandish spring constants, and things should be a lot more manageable. So we need to test it, of course, but one of the things we're going to have to look at is the strain immediately above and below the climber as it ascends. So above the climber, we're expecting that the strain should be slightly higher than the nominal. So the strain we've set out is 0.0625 at the start, and then that would be expected to slowly decrease as the climber ascends. So what you're doing is transferring mass from the upper part of the tether to the lower part of the tether, and below the climber, the strain should initially drop because you're transferring mass from above to below. You're making the tether below the climber slack, or let's say you're reducing the tension. And then eventually it should recover to near its initial value, and then this should slowly increase with time as the climber climbs. So the difference of the upper and lower strain should be proportional to the effective weight of the climber, that is, the gravity minus its centrifugal forces. And here's one of the first results. So on the horizontal axis is time in units of 120 seconds, I believe. And the upper line is the strain immediately above the climber. The lower line is the strain immediately below the climber. And as expected, above the climber, it's almost constant. On this plot, you can't see any variation. So that's good, and it's right where it should be, 0.065. If you go to the lower curve, you see that, as expected, you start climbing and it starts putting mass to the lower segment, and the strain is temporarily decreased until you reach a point where the strains equalize again, and it reaches the 0.0062, once again, as expected, for below the climber. So as I mentioned, lots of complications added. This introduces artificial boundaries, and you have to deal with that. As I said, you can do it by merging pieces of the tether together. The equations of motion become stiff. So as I mentioned, in this case, the spring constants become very large. Either you have to have very, very small step sizes, or things become unstable. And so we do the merging to take care of this situation. And we can test this for looking for any large oscillations in the strain. Ideally, you don't see any oscillations when the climber crosses a boundary, because after all, the boundaries are artificial. But if they're too many or too big, we need to go to another model. And here's what happens when you cross a boundary. So it's like the previous plot. We've gone now higher up, and this is 9,000 seconds, about 2.5 hours running. And there's about a small 2% drop in the upper strain as it crosses the boundary. So this is not supposed to be there. It is small. It does go away or fade away slowly as you go higher, but it's still there. Oscillations typically in the lower one look to be about 15%. And once again, they eventually die away with time and altitude. So neither effect is real. It's a result of the model, and what we need is to refine the model so that we can get rid of these. And once again, we just go a little higher. This sort of demonstrates that the oscillations do decrease as you go up, and you cross another boundary at 18,000 seconds, and you can see what happens there. We've got another drop in the upper strain, and oscillations are reintroduced in the lower strain. Now, the transverse motion. So we've up to now been talking about the longitudinal motion in the tether, how it stretches and compresses and so on. But because there is a Coriolis effect, we are going to be forcing the tether off to the west. So this would be negative y coordinate in my system here. So this is going to be proportional to the climber velocity. And it should develop, the tether should develop a kink. In other words, the slope in the tether should be fairly large or relatively large below the climber and get smaller above the climber. And this is also a good check for artificial oscillations. So to check that, what I've done here is looked at the Y deflection at the climber. So once again, the horizontal axis is time. The vertical axis is in kilometers. So that's 0.25 kilometers, 0.51 kilometer. And most of the motion, as you can see, is off to the west, that is to the negative. And this was run for a simulated 20,000 seconds, 5.6 hours. Now, generally speaking, it's doing what it should. The climber is going off to the west, going negative. Some interesting thing has happened at small times, and that is that the climber actually initially heads to the east. Okay, that puzzled me for a minute, but then what I have to do in the Lagrangian is to put in a term that accounts for the fact that the mass of the segments is changing. And so you have mass being moved from the upper part to the lower part below the climber. And that means that, oh, there's some little bit of mass that's going down instead of up. And that causes, of course, a kind of a reverse Coriolis effect, but only for a little while, and then it starts going back to the west again. And unfortunately, there is a rather large bump at 2.5 hours, 20%, but it gets smaller, 5% at 4 hours and 2% at 5 hours. So the trend is right, but once again, we really do need to get rid of those those artifacts. And my longest run yet is to look at what happens at the apex anchor as a function of time. Over here you see a plot of the x coordinate. In this case, the x coordinate is the coordinate. Yes?
2 minutes.
Oh, okay. In this case, the vertical is the x, so this is up and down, vertical, and the y coordinate is east-west. And right now you can see that, as the climber starts to climb, it pulls down the apex anchor. And it continues to pull it down until you reach about minus 80 kilometers. So that's quite a depression in the altitude. And on top of that, you can see superimposed some oscillations. And these oscillations happen to directly correspond to the first normal mode of the longitudinal oscillations. And so that was gratifying to see that that's coming through correctly. Also, you notice that we're heading off to the west rather quickly as the velocity of the climber increases. And so as I'm doing the simulation, I'm worried, is this thing going to fall over? But no, in fact, it starts turning back to the east. And so it's starting an oscillation. This is a much longer oscillation, and it's basically the full body oscillation of the entire tether, and we call this the libration mode. And based on what I've run so far, it looks like the frequency of that mode is about right, about 8 days to go one full swing to the west and then back to the east again. So those things are very encouraging. It looks like it's acting physically. So I was quite happy to see that. And we've run quite a long simulation test. And at this rate on my Mac, I think we can run all the way up to Geo in about 5 hours of CPU time. That's wall clock time. This particular simulation was 2.5 hours. All right, so we have completed the first space elevator mass model with distributed mass and mergeable springs. Looks to be numerically stable. That's great. We have all the correct physical effects, strain differentials, strain changes, Coriolis effect. We do, however, have some oscillations, which are artificial. Need to get a way of getting around them, making them smaller or making them disappear. So I consider this to be a workable early model. We can actually, even despite the oscillations, we can still use it for understanding some things we want to learn about how the space elevator moves as the climber goes up and down. What's next? We want to examine the tether shape, or that is the snapshot of the entire tether versus time. We want to look at all the normal modes, both transverse and longitudinal, compare those with what's been done so far. Torsion, density waves, EM effects, all of these need to be studied. I think this model could handle a few of those, but right now torsion is not built into it. We need to remove the discontinuities. And finally, we want to compare this to other codes, so especially GTOS, GTOS-JD, the Jorgensen-Potamia model, which is a point mass, massless spring model. And then there's also the Stephen Cohen model for space elevators. So things look good. We have things to compare to. And here is what I meant by the climber shape. So this is from GTOS. And there's the kink down there where the climber is. And that is what the climber should look like, a snapshot at a given time. So we would like to compare to that. And from Jorgensen and Potamia, they did a study of a charged tether because it's in a radiation environment, it's going to pick up charge, and therefore it's going to move in solar storms. And these are oscillations that they predicted based on a big solar storm, and this is something that we could compare to as well to see if our models are working. So that's it.
Looked the climber you put on there is a 20-ton climber, right?
That's correct.
And it looked like the apex moved 1,000 kilometers.
Yes.
That's pretty significant, isn't it?
It's, well, yeah, I mean, it goes down 80, which is no big deal out of 100,000. But 1,000 to the west, yes. That's still a pretty small angle. So, 1,000 kilometers out of 100,000.
Yeah.
But yeah, it is a big movement. And it's going to continue doing that unless you find a way to damp out the libration mode.
You didn't do the full trip to Geo, did you? So that you didn't see the recovery backwards and then the swing to the left. So we really need to see the whole picture. Yes, it swings that far, but it's way out there and you can plan for it. You can use the apex anchor unreal reel in to compensate for it in real time so you can straighten that out. There are a lot of ways to do it. We have to understand the full cycle, not just what'd you do, 500 sec? No, whatever you did that.
320,000 seconds, so 2.5 hours. And yeah, right. It does swing back. So this plot shows it swinging back, which was very encouraging. And now you just have to continue for another 3 hours or so to go to the other side, back to the east, where we hope it swings back yet again. So yeah, right. We do have to run longer.
Yeah, everybody who's done it in the past shows that it's stable in the overall sense with motion. So we need to understand the motion, definitely. But, then there's ways to compensate for the motion. There's ways to change the velocity and direction of the tether climber if we need to. So we have to understand the dynamics first, and then we have to figure out how to operate.
Mm-hmm. Right.
Jim's had his hand up for a while. Jim, you want to ask your question?
In the chart that had those series of humps that you thought were errors in the system, I believe they're correctly there. What is causing, that slide there, what is causing the humps is you have a tension wave induced by the acceleration of the climber on the tether, and it's moving back and forth on the tether, and that I think is as it changes direction, the mass flow on the tether as it moves outward and inward will produce those humps. If you look at the time difference of them, you'll see that it approximates the traverse time from the along the length of the tether between the climber and the apex anchor. So I think that those are real values in your report, in your chart, as opposed to artifacts generated by some error in your algorithm that you set up for calculation.
Well, that would be great, but what bothered me is that they occurred exactly at the time when the boundary crossing happens.
Then I would concur with you that there is an issue there.
Yeah.
That it may be in how you transfer the strain from the two pieces into the single piece,
Yeah.
and how that affects the motion of the
Then-
of the system.